Imagine waking up to a sky that no longer looks normal. At first, it starts as a few strange streaks of light crossing the atmosphere. Then more appear, then hundreds, then thousands. Within hours, observatories around the world confirm something that should be impossible. Every asteroid that could strike Earth is now on a collision course, and they are all arriving at once. Not one asteroid, not a regional impact, not even the kind of event that wiped out the dinosaurs. This is every possible impact happening together, from smaller bodies that explode in the sky like giant bombs to larger asteroids capable of tearing open oceans, igniting continents and choking the atmosphere. In real life, NASA says no known asteroid larger than 140 meters has a significant chance of hitting Earth in the next 100 years, and asteroid expert Davide Farnokia has said our calculations don't show any impact risk for at least the next 100 years. So this video is not a prediction. It is a thought experiment built on real impact physics and real planetary defense science. That matters, because the scenario is fictional, but the damage mechanisms are not. NASA's impact risk materials show that large impacts and airbursts can generate destructive blast waves, thermal damage, tsunami hazards, and, in the biggest cases, global effects. And if you enjoy exploring massive what-if scenarios like this, make sure to subscribe and turn on notifications, because on this channel we break down the most extreme possibilities in the universe. The first sign: the sky stops looking normal. The first thing humanity would notice would not be the impacts themselves. It would be the sky. Astronomers would detect an impossible pattern across the inner solar system. Objects that had once followed stable orbits would now be shifting onto intersecting paths with Earth. At first, scientists would think the calculations had to be wrong. Then, observatories in different countries would confirm the same numbers. Radar systems would begin tracking incoming bodies in quantities so large that even experts would struggle to describe the scale without sounding unreal. At night, the sky would fill with moving lights. Some would be faint. Others would brighten hour by hour. The world would realize quickly that this was not a meteor shower. This was planetary bombardment. Governments would issue emergency statements, but there would be no meaningful response plan for something like this. NASA's planetary defense work is built around early detection and deflection of individual dangerous objects, because one serious impact is already enough to justify global planning. Lindley Johnson, NASA's planetary defense officer, described DART as part of the toolbox needed to protect Earth from a devastating impact by an asteroid. But a scenario involving every asteroid at once would overwhelm any realistic defense system before the first major strike even arrived. Then the first wave would hit. The small asteroids. The opening assault. Many people might assume the smaller asteroids would not matter. After all, tiny meteoroids hit Earth constantly and usually burn up harmlessly in the atmosphere. NASA says small asteroids impact Earth routinely, often disintegrating in the atmosphere or falling as meteorites. But this scenario is different because it is not one object. It is saturation on a planetary scale. The atmosphere would light up almost continuously as countless smaller asteroids entered at enormous speed. Many would explode as airbursts. According to NASA's impact risk materials, airbursts and impacts can produce destructive blast waves and thermal heat that cause injuries, fatalities, structural damage, and fires over wide areas. So the opening phase would look like the whole planet had been placed under bombardment from the sky. Windows would shatter across cities. Buildings would collapse from repeated overpressure. Fires would ignite in neighborhoods, industrial zones, forests, and grasslands. Some objects would reach the ground in crater roads, airports, ports, farmland, and major infrastructure. Communication systems would begin failing almost immediately. Emergency services would be overwhelmed in minutes. Even before the largest impacts, civilization would already be breaking down. when the big asteroids arrive. The true catastrophe begins when the larger asteroids strike. A large asteroid does not hit the ground like a falling rock. It arrives with kinetic energy so immense that the crust behaves like a fluid under the force. Rock vaporizes, shock waves race through the planet, fireballs rise into the upper atmosphere. NASA's hazard models treat larger impacts separately because they move beyond local destruction into regional, continental, and global consequences. Now imagine multiple strikes of that kind happening nearly together. One impacts the Pacific and sends colossal tsunami systems racing toward Asia and the Americas. Another slams into a continent, vaporizing a city and blasting superheated debris across an entire region. Another hits near a tectonically active zone, producing seismic waves that destabilize already stressed faults. Another strikes the Atlantic, sending walls of water toward Europe, Africa, and the east coasts of the Americas. At that point, there is no safe hemisphere, no untouched ocean, and no meaningful difference between near and far. The whole planet becomes part of the disaster zone. The oceans turn into weapons. Because Earth is mostly ocean, many of these asteroids would strike water. That would not soften the catastrophe. It would globalize it. NASA's impact assessments include tsunami-affected populations because ocean strikes can drive major coastal devastation. Water would be flashed into steam, seafloors would be disturbed, and immense waves would radiate across entire ocean basins. Coastal cities would be erased. Ports, refineries, naval bases, shipping infrastructure, desalination systems, and coastal power networks would be destroyed in hours. And because impacts would be happening in multiple oceans at once, some coastlines could be struck repeatedly as wave systems crossed and collided. Saltwater contamination would spread inland. Agricultural land would be ruined. Freshwater systems would fail. The oceans would not protect Earth. They would multiply the destruction and carry it into every coastal civilization on the planet. The atmosphere becomes a weapon. After the shockwaves and tsunamis comes the next layer of horror. The atmosphere itself turns against life. Large impacts throw dust, pulverized rock, soot, steam, and chemically reactive gases high into the atmosphere. NASA's hazard models identify thermal damage and global effects as real consequences of major impact scenarios, and scientific studies of ancient impacts show why. Research on the Chicxulub event and later climate modeling found that soot and aerosols from impact-driven fires and target rocks can block sunlight, cool the planet, and suppress photosynthesis. One Ocher-hosted study concluded that soot is especially effective at preventing photosynthetic activity, while other studies describe global darkening and severe cooling after major impacts. But before the darkness comes, there is heat. Falling ejecta from major impacts would re-enter the atmosphere and radiate heat back toward the surface. Forests would ignite. Grasslands would ignite. Already damaged cities would burn. Fuel depots, chemical plants, and pipelines would become secondary fire sources. The sky would not just rain destruction, it would bake the surface on a global scale. Breathing outdoors would become dangerous almost everywhere. Smoke, ash, fine dust, and toxic gases would fill the air. Sunlight would dim. The sky could remain red, gray, and black for days, then months. The ground starts hitting back. Asteroid impacts do not only destroy the surface, they send enormous energy into Earth itself. Massive strikes would generate seismic waves powerful enough to trigger earthquakes far from the impact points. Already unstable slopes would collapse. Coastal shelves could fail. Volcanic systems under stress might be nudged toward eruption. Scientists do not treat every impact as a volcanic trigger, but the broader point is real. Impacts create cascading hazards, and hazard reviews emphasize the long-term downstream and secondary effects of asteroid strikes, not just the immediate crater. In this scenario, Earth would no longer be experiencing only asteroid damage. It would begin amplifying the event through its own tectonic and environmental systems. Landslides, fires, flooded coastlines, toxic runoff, collapsed dams, and ruptured industrial zones would turn impact damage into a self-feeding chain reaction. Impact winter, the real endgame. The immediate impacts would kill on a massive scale, but the long-term aftermath would be even more devastating. This is where the science becomes most sobering. Studies of the dinosaur-killing impact and later climate simulations show that soot and aerosols can drive an impact winter, sharply reducing sunlight and pushing global temperatures downward. One major study found that photosynthesis in the oceans could fall to near zero for many months after a large impact, while other work describes global darkening severe enough to collapse marine and terrestrial food webs. More recent research on smaller Bennu-type scenarios still points to serious drops in ecosystem productivity and global food security after a large impact. Now scale that up from one major asteroid to all of them. Crops would fail, plankton would crash, marine food chains would collapse, livestock would die from starvation, cold, and contaminated water. Transportation networks would already be gone, so even surviving food stocks could not be distributed. Humanity would not just face a disaster, it would face a planetary famine in darkness. The world after the impacts would not be a world of quick recovery. It would be a world of ash, cold, hunger, disease, and collapse. What happens to humanity? The honest answer is brutal. Most of humanity would die in the opening hours, days, and months. Some would die in direct strikes, others in blast waves, fires, tsunamis, structural collapse, toxic air, and contaminated water. Those who survived the first stage would enter a second stage defined by famine, cold, disease, and conflict over the last remaining resources. Some hardened underground facilities might preserve small populations for a time. Remote inland areas could fare better than coastal megacities during the initial strikes. But long-term survival would depend on controlled agriculture, clean water, air filtration, medicine, and social stability. In a world where sunlight is reduced and global supply chains are gone, that becomes extraordinarily difficult. Earth as a planet would survive. Human civilization almost certainly would not. Why scientists take even one asteroid seriously? This is exactly why planetary defense exists. NASA tracks potentially hazardous objects, issues warnings, and practices impact scenarios with emergency planners because even one sufficiently large asteroid could devastate a region, or worse. As NASA notes, early detection is critical if deflection is ever needed. And while no known large asteroid currently threatens Earth in the next century, the agency still treats impacts as a real natural hazard because the consequences of a large strike are so severe. So no, every asteroid is not going to hit Earth at once. But this thought experiment reveals something important. Our planet is not safe because impacts are impossible. It is safe because space is vast. Dangerous objects are relatively rare, and scientists are watching. Take away that luck for one day, and everything changes. The most violent day Earth could ever see. If every asteroid hit Earth at once, the result would be the most violent event our planet has experienced since its formation. The sky would burn first. Then the ground would shatter. The oceans would rise as weapons. Fire would sweep across continents. Dust and soot would block the sun. Food chains would collapse. Civilization would fall, and the survivors, if any remained, would inherit a cold, dark world fighting to breathe. Earth would endure. Life eventually might return and evolve again. But our world, the one built on stable seasons, breathable air, predictable oceans, and the illusion of permanence, would be gone. And that may be the most unsettling truth of all. Earth feels invincible only because most of the time, the solar system misses us.